Today we are going to learn about enhancing semantic segmentation with transfer learning. We will explore how to leverage pre-trained models to improve segmentation tasks, reducing training time while enhancing accuracy. You will gain practical skills in selecting and adapting models, fine-tuning strategies, and understanding domain adaptation techniques.
Welcome to our video on enhancing semantic segmentation with transfer learning. Transfer learning is a powerful technique in deep learning where a model developed for a particular task is reused as the starting point for a model on a second task. This method is particularly useful in semantic segmentation, a process of partitioning an image into segments to simplify or change the representation of an image. Today, we'll discover how transfer learning can improve semantic segmentation models by reducing training time and enhancing accuracy. By the end of this video, you'll be equipped with practical knowledge to leverage pre-trained models effectively. To start, let's delve into the basics of transfer learning within the scope of deep learning. Transfer learning involves taking a model trained on one task and applying it to a different, yet related, task. This approach is particularly beneficial in deep learning due to the vast amount of data and computational resources required to train large models from scratch. By leveraging the knowledge gained from previous tasks, transfer learning can significantly reduce the time and resources needed for training. It also helps in achieving better performance when the amount of available data for the new task is limited. Some common applications include image classification, natural language processing, and now, semantic segmentation. The ability of transfer learning to enhance training efficiency makes it a cornerstone in modern AI development. Semantic segmentation poses several challenges, such as the need for precise pixel-level labeling and a large amount of data for training. This is where transfer learning shines. By using pre-trained models, we can address these challenges more effectively. Transfer learning reduces the training time significantly because the model doesn't start from scratch, it already has a foundational understanding of visual features from previous tasks. This method also enhances model accuracy, as it can leverage the patterns and features already learned. Successful applications of transfer learning in semantic segmentation include medical imaging, autonomous vehicles, and satellite image analysis. These examples highlight how transfer learning not only accelerates the development process but also leads to more robust and accurate segmentation models.
Choosing the right pre-trained model is crucial for the success of your segmentation task. When selecting a model, consider factors such as the dataset it was initially trained on, the architecture, and the model size. Popular pre-trained models for segmentation include VGG, ResNet, and Inception, each offering unique advantages. For instance, models trained on large, diverse datasets like ImageNet tend to generalize better. The architecture of a model affects how well it can be adapted to new tasks. A model with a more complex architecture might capture intricate details better but could also be more computationally demanding. Lastly, assess the model's performance on benchmark tasks to ensure it aligns with your project's needs. Once you've chosen a pre-trained model, the next step is adapting it for your specific segmentation task. This process involves several key steps. First, customize the model's layers to suit your task, which may include freezing some layers while fine-tuning others. Feature extraction is an important aspect, as it allows you to utilize the model's learned features while focusing computational resources on the task-specific layers. Adding new output layers that match your segmentation requirements is essential, as it enables the model to produce the desired segmented output. Adjusting learning rates during training can help stabilize the adaptation process, ensuring that the model learns efficiently without overfitting.
Fine-tuning is a critical stage in adapting a pre-trained model to a new task. It involves carefully adjusting the model's parameters to optimize performance. Begin by identifying which layers to freeze and which to make trainable. This balance is crucial, as frozen layers retain the learned features, while trainable layers adapt to the new task. Fine-tuning requires a strategic approach to learning rates. A schedule that starts with lower rates and gradually increases can help stabilize training. Consistently monitor the model's performance on validation data to assess the effectiveness of your fine-tuning strategies. Adjust these strategies as necessary to achieve the best results.
Domain adaptation is a specialized area within transfer learning that addresses the challenges posed by domain shifts, where the source and target data distributions differ. Techniques for overcoming these domain gaps include using domain-specific data to fine-tune models and making architectural adjustments that account for domain shifts. It's crucial to understand the domain-specific nuances and incorporate them into your model's learning process. Successful examples of domain adaptation can be found in applications like cross-lingual sentiment analysis and adapting visual models from synthetic to real-world images. These techniques enable models to maintain high performance despite variations in data distributions.
Evaluating the performance of transfer-learned models is crucial to ensure they meet the desired accuracy and efficiency. Use metrics like intersection over union, IOU, and pixel accuracy to assess segmentation quality. These metrics provide insight into how well the model identifies and segments different regions of an image. Additionally, evaluate the model's computational efficiency to determine its suitability for real-time applications. Transfer learning often results in improved performance, however, continuous assessment is necessary to maintain and refine model quality. Implement strategies such as cross-validation and monitoring on unseen data to ensure robust performance over time.
Let's explore a case study that demonstrates the application of transfer learning in semantic segmentation. Consider a project involving the segmentation of urban street scenes for autonomous vehicles. The team began by selecting a pre-trained model trained on a large dataset of diverse images. They then adapted the model by customizing layers to recognize street-specific features, such as road markings and vehicles. Fine-tuning was performed with urban-specific data to adjust the model's understanding of the environment. Challenges included handling varying lighting conditions and occlusions, which were addressed through data augmentation strategies. The outcome was a significant improvement in segmentation accuracy, enabling more reliable navigation for autonomous vehicles. This case study highlights the practical benefits of transfer learning and the importance of adapting models to specific domain requirements.
As we conclude our exploration of enhancing semantic segmentation with transfer learning, let's recap the key insights. Transfer learning offers a significant impact on segmentation tasks by reducing training times and increasing model accuracy. By selecting appropriate pre-trained models, adapting them to specific tasks, and employing effective fine-tuning strategies, we can maximize the potential of transfer learning. As this field evolves, there are exciting opportunities for further advancements, particularly in domain adaptation and real-time applications. We encourage you to explore these concepts further, leveraging the resources and knowledge shared in this video to enhance your own projects. Thank you for joining us on this journey into the world of transfer learning.